So, hello guys. Sorry for the slight delay in the starting the session. I was facing some login issues on Teams. So, maybe we'll start in like 5 minutes so that a few others can join the session. So we can start discussing like problem change related to this week in like 5 minutes. Okay, so I guess we can get started. I don't think anyone else is joining the session. So first of all, hello to everyone who's present in the session. So uh, just to reintroduce myself, I'm Lakshay Saggi, the problem solving TA for the NPTEL Social Network Analysis course for the Monday 6 to 8 p.m. sessions. And this will be our third session for this course this semester. And in this session, we'll be mostly discussing like again, like previous week also, I think we discussed the focus was in the problem solving sessions, less on the problems, but more on the revision of concepts which were discussed in the previous week because there were a lot of new definitions and concepts thrown around for you guys. So similarly, this week also, because we are just getting familiar with like different kinds of social networks and everything. So this week also, there were a lot of like different types of models and different kinds of stuff introduced to you guys. So yeah, probably the problems based on those models will be easy, but we really need to get a better understanding of the models which were covered this week. So again, today also we'll be like doing sort of like a significant part of today's session will be spent on like discussing the different models which were discussed in this week's lecture. So like I've just taken out some of the important slides from this week's lecture videos, and maybe we can discuss them first, and then we have some problems related to uh, these models which were discussed this week. So mostly like models of random networks were discussed. So yeah, let's get going. So I'll just share my screen and maybe we can get started. Also, just a reminder, like if there are any issues with my audio or with my screen, or if there are any doubts in between, feel free to ask me via chat. Like, you can ask me anytime and I'll try to answer it to the best of my capabilities. So yeah, let's get started then. I'll just share my screen. Okay, so I hope my screen is visible to everyone. So this week, the focus was mostly on real world networks and how do we model these real world networks. Uh, Firstly, we started with uh, some important properties of real world networks. Like first, if we want to model a real world network in a theoretical sense, then first we need to know which properties do we want out of our theoretical network. And it was established that there are three very important properties followed by real world networks which we would want our theoretical networks to imitate to also imitate, and those properties are something like always real world networks tend to have high average local clustering coefficient. And what is like average local clustering coefficient? We already know what is a local clustering coefficient for a node. For a node, local clustering coefficient is nothing but like the number of edges between the neighbors of that node divided by total number of possible edges between the neighbors of a node. So that will be local clustering coefficient of a node. This we discussed last week also. And what will be then average local clustering coefficient? So if you take average over all the nodes, the values of local clustering coefficients at all the nodes, if you take the average of those, then you'll get an average local clustering coefficient. And real world networks usually have a very high average local clustering coefficient. Second property which real world networks tend to have is a small world property. So this is a really cool property which says that average distance between any two nodes in a real world network is quite small. So like in general, like this is like a pretty cool fact, and you may already know this. It is usually said that for any two humans present on Earth, like if you want to find a chain of friends, so like how far are two humans based on their chain of friends. So like if there is a person living, let's say in India, and there is a person living in America who are totally unrelated, who do not know each other at all. So usually on average, if you have six people in the chain in the middle, so approximately like the US guy will probably be a friend of 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 a friend. Maybe like friend of a friend like this six times. So like and usually like usually, so what this means is using small world property, like to any two arbitrary people, uh, any two random people, and two people chosen at random will probably have a chain of friendship of length at most like 6 or 7. At least this is true in like this was a social experiment which was done by some scientists. I don't remember the name, and like yeah, this was found to be kind of true that our world possesses this small world property, which I find pretty good. And then the third property of real world networks is the scale free property. And scale free property is nothing but it says that real world networks tend to follow power law. And we discussed last week also what do we mean by, so maybe I should just add this. So, no. So that scale free property, what does scale free property mean? Scale free property means that real world networks tend to follow some power law. So power law can be like power. So we discussed what are power laws. Power laws are basically number, the fraction of nodes of degree k should be proportional to the value k itself, or like maybe k square or something. The number of nodes in a network appearing with like number of nodes with degree k in a network should be proportional to like degree raised to the power something like. So different kinds of power laws can be like, so one power law can be where number of nodes are proportional to like, let's say number of nodes of degree k is proportional to k raised to the power minus half. Some in some networks it can be k raised to the power minus 3, k raised to the power minus 2, and so on. And it was discussed in this week's lectures that we'll discuss some networks which follow this kind of power law property. Like, it was discussed in this week's lectures also, but we just do it again. So scale-free property is nothing but if the network follows a power law, some kind of power law, then uh, we say that the network is scale-free. So these are the three properties which we will want to model in a theoretical network so that it mimics the real-world networks. So what is small world property? I already discussed this. So this was an outcome of Stanley Milgram small world experiment. So yeah. A network is held to follow small world property if the average path length of the network is logarithmically proportional to the network size. So while discussing with you, like I said that usually there's a small distance between any two nodes chosen at random. So how do you quantify this small? So in a network with, let's say, n nodes, you will say that if there are log n, if the average path length between any two nodes is log n, then you will say that the network has a small world because log n is quite small as compared to n. And so like this 6 degrees of separation model is what I was telling you guys that that about that two people chosen at random are about like 6 friends away from each other. And approximately like you can model this as, so if the world's population is, let's say, 10 to the power 6 or something, although it's quite larger than that, but like log of 10 to the power 6 is something like 6 only. So that's why you can kind of say that our real world follows this small world property. And then what's the scale free property? So the three kinds of properties which we wanted was this high average local clustering coefficient. This we already know what it is. Local clustering coefficient we discussed previously and today also. Then we discussed the small world property, and now we come to scale free property, which just means following some kind of power law. And what is like in general definition of a power law? A relative change in value of one variable leads to proportional change in the value of other variables. So mathematically, like y is proportional to x to the power minus b, this will be some kind of power law. And specifically in real world networks, the power law which we'll be interested in will be the number of nodes, the fraction of nodes of with degree k. So in real world networks, the power law which we want is like this y will be the fraction of nodes of degree k. And this x will be the value k itself. So fraction of nodes with degree k should be proportional to k to the power minus b. where B will be some real world, where B will be some real number, and this will be different for different models which we have. And why do we usually call this a scale-free property? Because yeah, the functions that follow the Bower law are kind of scale invariant, because like the quantity here, like y divided by x to the power b, will always remain a constant. So y divided by x raised to the power b, or y multiplied by x raised to the power b, will always be a constant. And that's why it's kind of scale invariant. You know that if you multiply y by 10, then uh, re uh, x will reduce by 10 raised to the power b or something. So yeah. So power laws are kind of observed in real world networks. That's why we tend to model theoretical networks which actually follow power. So now let's come to maybe the first kind of networks. Like okay, so note that like Rome wasn't built in a day, right? So while modeling real world networks, it's not that in the first try itself people got some kind of people realized that there exists a theoretical network which can mimic real world networks. So initially people tried some kinds of models, and those models followed some kind of properties which were like not sufficient, like all of which followed like out of three, maybe one or two properties, but like we wanted three out of three properties. So people improved upon those networks and realized theoretical networks which followed like more properties, and then like uh, nowadays we have like very refined theoretical models for real world networks. But like one of the first networks which was proposed was, although this was quite nice, it did not follow like all the properties of real world networks, but it's still important because it was one of the earliest network models which was proposed. And this was like Erdos and Renyi model, and which is just a random network model. And there are two kinds of variants for this ER. So Erdos Renyi model is also called ER model. So there are two kinds of variants for this. You probably would have seen this in lectures also. So basically, what the model says is that it's a completely random network model. And what this means is uh, yeah, so you can characterize this randomization in terms of number of edges or with respect to some probability factor. So one variant of this model can be, suppose you have two parameters for the model which you input, which is n and k, and then what will be the graph? So graph will be from set of all possible networks of n nodes and k edges. It chooses one network at random. And another way of saying this is the second kind, where you say that network has n nodes, and any random pair of nodes has a probability p of being adjacent to each other. And this p is independent, like it does not depend on any other thing. So to construct a like a G and P graph network, what you have to do is like just generate a graph with n nodes, and between every pair of nodes, like sample an edge with probability p. And these two variants are kind of equivalent to each other, as you can observe. Also, if you set p equal to k by n, then the expected number of edges in the second variant, the Gilbert's variant, will also be equal to k. So both the variants kind of behave identically in the limiting case, and that's why this usually the GNP model is considered as the standard random network, because this is easier to deal with because we have kind of independence between the edges and so on. But yeah, I hope you guys understand like what's this random network model. If there are any doubts, feel free to ask me in chat. Okay, so maybe just like quick question to you guys, just a probability kind of question. So maybe um, so this is kind of a trivial exercise. So what will be the okay? What should I ask? What do I? Just a second, guys. Let me frame this question, and it would be an interesting question for everyone. So yeah. So maybe what I'll do is so if you guys remember like last time when we discussed something like a local clustering coefficient and a global clustering coefficient, and what was the value of global clustering coefficient? It was something like a number of uh, closed triangles divided by number of open triangles plus closed triangles, right? It was called triangles, right? So what will be the expected number of open triangles in a G and comma B network? And what do we mean by open triangle? Maybe just to revise. So open triangle is uh, three vertices A, comma B, comma C form an open triangle if like so three vertices are there A, B, C. So they can have maximum three edges A, B, B, C, and C, A. There can be three edges between these three vertices if only two of the possible three edges are present between them. Okay. So I would like you guys to try this out right now. Maybe it's a cool question, like not too hard also, and somewhat related to this week's assignment for you guys. So what will be the expected number of open triangles in a GNP network? And what's an open triangle? Three vertices ABC, any three vertices form an open triangle if only two of the possible three edges are present between them. So like this is an open triangle, like this vertex, and this vertex. Okay, no, this vertex, and this vertex. Because you can see that there is one edge here, there is one edge here, but there is no edge between these two. So this is an open triangle. So how many like open triangles will be there in expectation? Um, guys, would anyone like to try this out in chat? I would like, even if you're not sure about your answer, just try it and like try to write something in the chat. Let's be a bit more interactive. Or if there are doubts with the question itself, like what do I mean by an open triangle? Please ask that also. Maybe like I'll give you 2-3 minutes to think about this. So it's 6:32. Please try to. Even if your answer is incorrect, it's completely fine. I just want to uh, be a bit more interactive with you guys, and like maybe we can discuss like if your answer is incorrect, why is that incorrect, or like how would you go about it? I don't want to like directly give away the solution. So maybe like I'll give you 3 minutes, 2-3 minutes to think about it. Till then, I'll mute myself. If you have any ideas, just type in chat and we can discuss those. So this is the question. So what will be the expected number of open triangles in a GNP? So if there are n nodes in the network and each edge is present with probability p, then how many possible open triangles will be there? Okay, Karpagam. So Karpagam is asking any clue to answer this question. So maybe I'll give first hint. So hint one would be, so if you guys are familiar with probability, then you guys might know that like for any two random variables x and y, expectation of x plus y is nothing but equivalent to expectation of x plus expectation of y. So like you can always separate out the expectations, right? So what this implies is suppose if you have a random okay, maybe I'll just write this down. Yeah. So what this implies is expectation of uh, number of open triangles is equal to probability that ABC form an open triangle. Probability that ABC form open triangle times 1. Over all possible triplets ABC in V. ABC so like what I mean is like, so what I mean to say is so like if you want to find out what is the expectation of number of open triangles. So number of open triangles is nothing but basically uh, what you can have is like suppose you take all the triplets of vertices in the graph. Suppose you have something like a comma b comma c, then you have c comma then you have something like d comma e comma f or something like that. Then either that triplet is forming an open triangle or it is not forming an open triangle, right? So what you can say is it forms an open triangle with probability P, like not with P, but this probability term is like basically saying that it forms an open triangle. And if it forms an open triangle, then it contributes a value of 1 to my overall sum. Because what is my overall sum? My overall sum is number of open triangles. And this is nothing but equivalent to like summation over all triplets. Uh, the value that the indicator variable which is 1 if like that triplet forms an open triangle and 0 if that indicator variable does not form an open triangle. Does this make sense? So and then like what's the expectation that a triplet forms an open triangle? It is just like probability that it forms an open triangle times. Does this make sense, Karpaga? Or should I try to explain this again? Uh, by yes, do you mean should I explain this again or? So, so maybe just to reiterate, like three vertices A, comma B, comma C are forming an open triangle if two of the possible three edges are present between them. And now let's see like what will the number of open triangles? It will be just equal to like sum over all the possible triplets, and maybe just take let's take sum over all the possible triplets and see whether that triplet is forming an open triangle or not. And then whether each triplet is forming an open triangle or not is just equal to like probability whether it forms. Okay. So now, so maybe let's discuss this right now. So actually, this term reduces to this thing like expectation of number of open triangles is equal to like sum of probability that ABC form an open triangle over all possible vertices ABC of G. So this sum term, maybe I'll just simplify this for you guys a little. So how can we write this sum term? So how many triplets of vertices are possible in G? So there are n vertices, and out of those n, we need to have 3 vertices and check whether those 3 form an open triangle or not. So choosing the first, so like selecting the first vertex has like n choices, second vertex has n minus 1 choices, and selecting the third vertex C has n minus 2 choices. Note that we want these 3 vertices to be distinct, right? So now we have that we have chosen this triplet, and now in this triplet, what we specifically want is this triplet should form an open triangle. And maybe like if this triplet is of form ABC, then it should form it specifically should form an open triangle, which like in which edges from B are present. So like the AB and BC edges are present and CA is not present. So then this will be like nothing but probability that AB, comma BC edges are present and CA edges not present. So something like this will be my value. Yeah, Karpagam. So it could be all possible triplets could be n choose 3. Yeah, maybe saying this as n choose 3 would be also a good idea. So maybe let's just write it as, okay, maybe I should not directly do this, although this also makes sense. Yeah, maybe I should write like this only. So we select any 3 vertices. So first we have selected maybe like n, maybe I should write this as n C3 vertices. And then after selecting this triplet, we have to say, so I should not write this, that probability that this triplet ABC forms an open triangle, right? And what does this equal to? So like now we'll try to reduce this probability term. So this n choose 3 is outside only. So we still have this n choose 3 term. And then, okay, I still have this n choose 3 term. And then we have that probability. So like if there are 3 vertices ABC which we have selected, then they can form an open triangle in 3 kinds of ways. So one way can be AB and BC edges are present and CA edge is not present. Another way can be like the open triangle is rooted at not at B but at A. So this term plus probability that A maybe like B comma A and A comma C edges are present and B comma C edge is not present, and plus similarly an open triangle which is rooted at C. So A comma C and B comma C edges are present and B comma A edge is not present. So we have to add up these 3 probability terms. Why is this the case? Because we have selected 3 vertices, and when after selecting these 3 vertices, like now we have to see in how many ways can an open triangle be formed. So note that how many ways can it be formed. So suppose we had a full triangle ABC, then you can have to remove one edge out of that. So either that edge removed can be like CA edge or BC edge or BA edge. So there are 3 choices for removing an edge, if this makes sense. So the number of open triangles will be equal to this, the expected number of open triangles will be equal to this expression. And then maybe now I have almost solved the entire problem for you guys. I really want you guys now to answer like what will be this term, because this term will be equal to this term and this term, because like all of these are identical, because like this ABC chosen vertices are arbitrary. So like the answer will be n choose 3 times, maybe I should just write it again. So these 3 terms, so this term, and this term will be equal, because like ABC are just arbitrary vertices. So then this will be equal to n choose 3 times 3 into this thing, probability that A, B, B, C edges are present and C edge is not present. Now what's the value of this? So Karpagam, would you like to answer this? Like maybe just try it out. Like what will be the value this? Okay. So let's just see. So as we already discussed, so what's this random network model, like this GNP model? So any random pair of nodes has a probability P of being adjacent. So every edge has independently a probability P of being present. So yeah, so what I mean is like this AB edge being present, BC edge being present, and the CA edge being absent, all of these are independent events because it's like the the ER model has this property that every edge is present with some independent probability. So what this term can be broken down into, so like if like AB edge is present, BC edge is present, and C edge is not present. So this term can be broken down into like three simpler terms. Like you can, like, instead of writing this as this, you can just multiply the probabilities of these independent events. Because note that if two events A and B are independent, then probability that A intersection B occurs is equal to probability of A times probability of B. This is like property of independent events. So like then this will be like probability that AB is present times probability that BC is present, BC edge is present, and then the third probability will be times CA edge is not present. That so AB was present, BC was present, and CA was not present. So CA was absent. And this can be broken down into like three independent terms because like probabilities in Ardos-Renyi networks are independent. So this will be like AB is present times BC is present times CA is not present. Yeah, so good job, Karpagam. So yeah, so first term with this will be P because this edge is present with probability P. This will also be P because again this edge is present with probability P, and this is not present with probability 1 minus P. So the answer then finally will be, maybe I'll just copy this again and substitute the values. So this AB edge being present has a probability P, then BC edge being present again has a probability P, and this edge is not present has a probability 1 minus P. Yeah. So you have a similar kind of question in your like this week's assignment also, but like a bit different, like not exactly open triangle, but I think it talks about closed triangle. But similar concepts will need to be applied to solve that problem. So good job, Karpalo. So the idea was maybe like to count the triangles, maybe let's just take any triplet and see whether that triplet forms an open triangle or not. And how many ways can a triplet form an open triangle? Either it can be formed by removing the edge CA, or removing the edge BC, or removing the edge BA. And so we summed up these three cases. These three cases are equivalent, so we just multiply it by 3. And then like for each of the case, we calculate the probability. And the probability is simply because all of these edges are independent, the probabilities of these edges present is independent. Like all of these just get multiplied. So this is our final answer. So n choose 3 is nothing but n times n minus 1, n minus 2 divided by 6. So this 3 and 6 will cancel out and we'll just leave 2. The final answer will be something like n. I won't write it down. I'll leave it at this, but the final answer will be something like n times n minus 1 times n minus 2 divided by 2 times p square times 1 minus p. So something like that. So I hope this makes sense to everyone, and we can move on now. So another a very interesting property which arises out of like Arduino networks is like emergence of giant component, and maybe like we won't into the derivation of this because it was discussed in lectures, and like we can't really discuss everything in depth in a 2 hour session, which was discussed over the course of a week. So we'll only be discussing the high level results and not the uh, actual derivations. You can see the lecture videos for them for those. So the important theorem where in those linear networks is a giant component emerges in a random network when the average degree of the network is greater than or equal to 1. So what's the average degree? Average degree is nothing but average degree means like taking like literally taking the average over all the degrees of the network. So if the average degree is equal to unity, which just means something like a number of edges in the network is something like maybe 2n or something, then yeah, then actually a giant component emerges in the net. So yeah, and like what this giant component means is like the giant connected component. What this means is that there exists one connected component with very high probability that captures like 90 to 95% of that. So 90 to 95% of the nodes in an ER network are present in one connected component. The average degree of the network is greater than equal. And like there are different kinds of regimes of evolution. So this is the second order phase transition. So this is not like, so the size of the giant component is not a linear growth. It's not like if the average degree was small, like if you double the average degree, then the giant component size also doubles or something. So it's a second order phase transition. So like it follows some complex mechanics, and you can see the derivation of why this is the case in the lectures. There are different kinds of regimes where like there's a subcritical regime where like if the average degree is less than 1, specifically less than 1, then a number of small isolated clusters appear. Whereas as soon as we reach the critical point, which is average degree of 1, a distinguishable component actually emerges. And as you increase the average degree even more, supercritical regime, then the giant component grows and less smaller isolated clusters are there. And if you increase the average degree even further to make it greater than log n, then giant component absorbs all nodes and component, and the whole network becomes connected. So if average degree is greater than log n, the network is entirely connected. There are no isolated clusters or anything. The entire network gets connected. So this log n is the transition at which entire network becomes connected, and this one is the transition at which a giant component starts to emerge. So okay, like this is a very important factor in networks which we should keep in mind. And then now we talk about like this. So we initially talked about 3 kinds of properties, right? In what that should follow a real world network, which are like clustering coefficient, uh, small world, and power law. Actually, it can be seen that Arduino networks actually follow only one of those properties, which is small world property. And like maybe we'll skip the derivation, but like in Arduino networks, approximately the average path length is nothing but equal to log n, where n is the number of nodes. So actually, like if you derive it, like this was discussed in the lectures, if you try to derive this going to derivation, then you will arrive at like Arduino networks will be following the small world property. But note that they won't be following. They won't be having high clustering coefficient or like the scale free or power law kind of property. Like here's a note which I left here that ER networks do not follow the power law property. And why is this the case? Because what's the degree of a node in an ER network? It's nothing but a binomial distribution. And I hope everyone knows what a binomial distribution is, because like what will be the probability that like maybe we'll just discuss this binomial distribution. Like, though this was discussed in the lectures, but we will discuss this again. So maybe we'll just try to do this by ourselves. So what's the probability that a node V in an network, probability that node V has degree equal to k is equal to. So like note that what's power law property. So power law property essentially says that we have to find this probability, and if like this probability is proportional to something like k to the power alpha or something, then we will say that power law property is being followed, or if it is not followed, otherwise. So what will be the probability, guys? Would anyone like to try this? Like, what will be the probability that a node V has degree equal to k? This is similar to the arguments which we discussed just in the triangle case. So I hope you guys can at least try this out. So Karpagam, would you like, or anyone else also, maybe Kalai, Vani, or Sneha? Like, what will be the probability that a given node V, so suppose you are given a node V, so it has a degree equal to k in the ER model. What will be this value? Like I already have the thing here, like it will follow a binomial distribution, but maybe if you don't know the binomial distribution, it's a good exercise for you guys. So again, note that maybe like since no one is answering, I'll just do this also. So again, note that the ER networks have a very cool mathematical property, which is like all edges are present independently of each other. So again, like we can like for different kinds of events, we can like instead of like taking A intersection B's kinds of events, we can just like multiply the probabilities of edges being present. So this is nothing but equal to. So what we want to do is so there are like n minus one. So if the whole network has like n nodes, then for the network, the node V can only have like edges to the remaining n minus one nodes. So there are remaining n minus one nodes, and out of those, we want to have degree to exactly k of those. So first we choose those k nodes to which we want to have a degree, like to which we want to have an edge. And then so out of the n minus one vertices, we choose like k vertices to which we want to have an edge. And then what will be the probability that like we have edges to exactly k of these vertices? Now I think like you guys should complete this. Like we have selected k vertices out of the n minus one vertices, and now we want that all of these k vertices should have an edge with v, and the remaining vertices should not have an edge with v. So what will be the probability term? Come on, guys, just maybe try this out. Like, it's completely fine to be like wrong because like it helps us understand things better. Maybe just please try this out in a couple. Like I'll give you like a couple of minutes. Maybe it's like 6:57. So try this till 7 p.m. Like, what will be the term after this? So we want to have like k neighbors. So first we select an arbitrary set of k vertices, and then what we want is like probability that the value of this probability term, where what is the probability that v has edges to exactly the selected k vertices. So we select some k vertices, and now we should have edges exactly to these selected k or k selected vertices. And now, like, I want you guys to find out. Tell me, like, n minus 1 choose k, repeat, and then Like, what will be this term equal to? Like if like in a near network, D and the parameters given to us are like n. So like this probability term will probably have to do something with P, because P is the probability with which an edge is present between two nodes. So would anyone like to answer this? Yeah, so I already wrote this like Karpagam, I already wrote this n minus choose k term. Like this is the term for like selecting the k vertices. And now we want to find out whether these k vertices are indeed like and then we want to find like this probability term that V has edges to exactly these k selected vertices. Like I have already selected the k vertices, and now I want to attach an edge to exactly these k vertices. So like selected term is correct. Like V choose k, or like I would say V minus one choose k, because like this, because the total nodes are n and one of the nodes is this small v, so like there are n minus one nodes remaining to which we can have an edge. So it would be n minus one choose k, and then we want to find out probability that in this case, in this set of k vertices, like I have an edge to exactly all of these. Oh yeah, Karpagam. So Karpagam says it would be something like p, not p times k, it should be p raised to the power k. Uh, does like that's also like not entirely correct, but maybe I'll just write down there. So let's say like maybe I'll just number these vertices as v1, v2 till the selected k vertices are like, let's say I'll call them as v1, v2 till vk. The k selected vertices which are v1 to vk. Let's call these k selected vertices v1 to vk. So we should have an h2 exactly v1 and also v2 and v3 and so on. So note that this is the event which we want to find the probability of. And now this can be broken down simply into, because like probabilities of edges being present is independent in an ER network. So it will be just be equal to V has maybe like I just write down that V comma V1 is an edge, and V comma V2 is an edge, and can be replaced by a multiplication because all these events are independent. So times V comma V2 is an edge, times and so on till probability that yeah, probability that V comma Vk is an edge. Yeah. So does this make sense, Prabhakar? And that's why like and then each edge being present has probability p, so you'll obtain something like a p times p times p times p for k, like k value, so you will obtain something like p raised to the power k. But is it the only thing? Like, is there something missing, or is this the only thing? like, like note that in that open triangle we said that like like two edges are present and one edge is also not present. Similarly here also we want that these edges should be present, v2 v1 v2 v2 and till v2 vk, all of these edges should be present, and all the remaining, like there are remaining n minus, so apart from this v1 to vk vertices, there are further n minus 1 minus k vertices, and we want that none of those vertices should have an edge. Probability that none of the remaining vertices have an edge to v. And so yes, exactly. Probability for those edges that do not have an like degree k. Okay, maybe not this exactly, Kirpagam, but like none of the remaining edges vertices have an edge to be. So this is what the probability will be, if it makes sense. Like we want that all of these edges should be present and all of these edges should not be present for V. And this will be nothing but so you can have this n-1 choose k, and you can replace all of these by p's. So maybe I'll just write down the whole expression. So this is n-1 choose k, and then this will be p, this will be p, this will be p, and this p will occur k times. So this will be nothing but e raised to the power k. And then for all the remaining like n minus k minus 1 vertices, you want that this edge should not be present. So it should be 1 minus p raised to the power n minus 1 minus k. So this will be the probability that a node has degree k in an ER network. And this is the basis of like all the calculations which we do in this. And this is note that this thing is called like a binomial distribution because it looks like a binomial term and something. So yeah. And yeah. So, and it was discussed in the lectures that as like the network becomes very large, so like if when this n goes to infinity, like this actually becomes equivalent to like this was mentioned in the lectures, like but it's a property of binomial distribution, or it's a property of this function itself, that as n grows larger, this becomes almost equivalent to Poisson distribution. And maybe like I won't get into Poisson distribution right now because like we have to discuss other stuff also, but you can see this in the lecture videos that as n goes to infinity, as n becomes very large, this distribution starts behaving like a Poisson distribution. So maybe you can look this up yourself, or the proof of this, or you can see this in the lecture videos also. So yeah, so maybe like just good exercise for all of us. And then okay, so first we discuss maybe the power law that ER networks. So first we discuss ER networks have a small world property, but they do not have power law property. And similarly, like a clustering coefficient in ER networks is also like not very large. And why is this the case? Like it can be like derived that local clustering coefficient for any node is nothing but equal to P itself. So local clustering coefficient is equal to P in a ER network GNP. And like what's P equal to? P is nothing but average degree divided by N. And note that average degree is usually small in our real world network. So like even as we saw like in ER network, even with average degree 1, large giant component appeared. So if you have like average degree as something like 1 or 2, it's sufficient for us to form like giant components. But if average degree is 1 here in this function, the clustering coefficient becomes equal to 1 by n. And this 1 by n is very small because as n grows larger, like this term becomes 0. So yeah, so the clustering coefficient is nothing but equal to P. And usually what happens is in a real world network, the average degree given to us is like quite small. So average degree is something which is given to us, and in form of average degree only we have to specify whether uh, this CI is good or bad. So if average degree is something like a constant here, let's say 2, 5, or anything like a 10, then the clustering coefficient is nothing but 10 by n. And as n grows very large, it becomes almost equal to 0. So clustering coefficient is inversely proportional to size of the network. And one thing to note is clustering coefficient in ER network does not depend on degree of the node. So it does not depend on degree of any node. It depends on the value of average degree, but not on specific degree of the node for which we are finding out the coefficient. For a node, it is just equal to P. So I hope this makes sense for everyone. So like clustering coefficient for any node depends just on average degree and inversely proportional to the size of the node. It does not depend on the specific degree of the node which we are considering. So ER network kind of follows like small world property, but does not have high clustering coefficient, and it does not have power law kind of property. So it satisfies only one out of three possible properties. Yeah. So yeah, there was a plot in the lectures that real world networks are often scale free, and like ER networks behave a lot more different. Maybe I should just remove this. Like it can be found in the next slides. And then so maybe we have satisfied one out of the three properties, but can we modify those to obtain some new model? So even though this ER model satisfied only one of these three properties, but it was a cornerstone result because like it allowed us to maybe build onto this ER network and try to make the network like have other properties also. And one thing for and one such like idea which was introduced was this regular ring lattice network model, where what it says is that suppose we have a network where all the n nodes are lying on a ring, and every node in the network is connected to exactly k other nodes. And what are these k other nodes? So in the ring, like for any node, you take the k by 2 rightmost elements and k by 2 leftmost elements and add edges to them. And then this will be a ring lattice network. So maybe for like this node, for this network, like every node has kind of every node is kind of connected to exactly two other nodes. So like one on the right, one on the left. Okay, maybe. Oh yeah, so it's connected to four nodes, like two on the right, so this node, and two on the left, so this node and this node. So every vertex here has degree 4. And so this is a 4 regular ring lattice network. And what's like the good thing about these ring lattice networks, maybe I'll just mention this. Like ring lattice networks have. So we'll try to now so in the ER networks, we only had like small world property. Now we'll try to modify ER networks so that they also have like good clustering coefficient. So one like ER networks have low clustering coefficient, but one good property of these ring lattice networks is that they have high local clustering coefficient. And what the value? So this was derivation for this was discussed in the network in the lectures, and like and the value actually is clustering coefficient can be as high as 3 by 4. So derivation for this was like you can in the lectures, but like as k changes, like with respect to k, the clustering coefficient also changes, and it can be like as large as 3 by 4. And 3 by 4 is a very big quantity because it's a constant. And whereas in a random graph, we just obtained it as 1 by n. So like 1 by n is inversely proportional to size. So here it is like independent of size of the network, the local clustering coefficient. Okay, so now we know that ring lattice networks, like although they won't have any small world property, because you can see that any two nodes which are diametrically opposite will have to travel a lot of nodes to go to this side. But we'll somehow introduce so this what this Watts-Krogat's network model does, it tries to somehow combine these lattice networks and ER networks so that we obtain one network which has best of both worlds. Like it also has small world property and also has a high clustering coefficient. And how is it done? Maybe it was ER networks possess the small world property but have small clustering coefficient. Regular ring lattice networks have high clustering coefficient but do not follow small world property. So this Watts-Krogas WS model forms networks that have high clustering coefficient and have the small world property. So it combines the two lattice model and the ER model somehow. And how is it done? Uh, maybe we should not discuss like how is it done, because yeah, I think I skipped this because like this is already available in lectures, and uh, yeah, you can see the procedure, but maybe we should just discuss the properties of this network. Like usually how is it done is like maybe I'll just give you a high level idea. So what you do is you start with a regular ring lattice network model, and then you try to like randomly change assignments of all of these edges to some other nodes. Maybe you can look it up in the lectures. Like that's exactly what's true as network model. But what are some really nice properties for this Watts-Square network model? Like it approximates to ring lattice networks if you like do something like so. There's a parameter beta associated with Watts-Strogat's network model, which is like the rerouting probability. If you know what this rewiring probability is, if you have seen the lecture. So if this probability goes to 0, then it's just a ring lattice network, and if it becomes 1, it's just an ER network. And like maybe I should just this is not really relevant to us, but this is something which is really relevant. The Watts-Strogat's network model uh, like has an average path length of some. So you can actually plot like normalized values and rewiring probabilities with respect to like. So you can actually plot like clustering coefficient and average path length in a WS network model, and you will see that initially the clustering coefficient is large, but the average path length is also large. So initially, when this probability p, which is on the x-axis, let's forget what this probability is about. But when it is small, we have that the average path length is large, but clustering coefficient is also large. Now, what we want to do is we want to decrease the path length, but we want to remain like clustering coefficient to be large. And this is like precisely what happens in a WS model as you go along x-axis. As you go along x-axis, the clustering coefficient remains large till this point, but average path length has reduced significantly. So this is kind of a sweet spot for us. Like this probability here is kind of a sweet spot for us because here clustering coefficient is large and average path length is small. So now it follows small world property as well as like high clustering coefficient. So yeah. So yeah, maybe this is the key takeaway, that if you like at one end it starts. So here like you can see that clustering coefficient is small and average path length is also small. So here it behaves more like an ER network. Here it behaves like a ring lattice, and somewhere in the middle it behaves like it satisfies like two properties of the real world networks. So that's why like this is a good model for us to work with, this Watts-Strogat's network model. Yeah, but still it does not like it can be like verified that this Watts-Strogat's network model also does not follow like power law. Like neither the ring lattice followed power law and neither ER networks follow power law. So yeah, so Watts-Strogat's definitely does not follow power law. So maybe like so till now like we have now taken like two of the three desired properties. So we have small world property. We also have like high clustering coefficient. Now we'll introduce a network which like allows us to have the third property also, which is the power law. And this is the Barabasi-Albert network model. And this is a model which actually starts evolving with time. It starts with a small tree network, and the network grows as new nodes and edges get attached to the network. And this is also called a preferential attachment, or rich gets richer model. And this generates like scale-free networks. So the idea in this network is like, if you guys don't remember, maybe I'll just describe it on a very high level. Like at every step of time, like some kind of node comes in, and now that node tries to like attach itself to the node which already has a very high degree. The higher the degree of a node, the more is the probability of a new node getting attached to that node. And now we model like how the network grows with time, and it turns out that this follows kind of a power law. Yeah. and the derivations and everything was kind of discussed in the lectures. So I'll not be going into those, but I'll just be maybe going into the final result. So where it was discussed that like degree of a node I at any time t is actually proportional to the time t raised to the power beta. Like in a Paravasi network model, so like this model starts going with time, and at every step of time, like t, like the degree of a node is like proportional to the time the node has spent in the model raised to power some beta. So beta is a constant, and it's I think equal to half something. I don't exactly remember, but you guys can verify from the lecture. And note that also, like this was also discussed in the lectures that uh, what's the first mover advantage? The nodes which were present initially in the network have like higher degrees. The nodes which are added later have lower degrees, and the rate of increase of degree is inversely proportional to square root of time. So it's something like yeah, like as the degree, like as time progresses, the rate of increase of degree like reduces. But like still the total value of like the degrees is higher, like as the model spends more time, as the vertex spends more time. And when we come to power law, power law is nothing but like saying that what's the probability that a chosen vertex will have degree k. So here it turns out that the value is equal to 2m square by k cube. So here like the power law is so the power law which is followed in this kind of Baravasi-Albert model is that pk is proportional to 1 by k cube. Like so basically a node has a degree of k. The probability that a node has a degree of k is proportional to 1 by k cube. And note that this is what we want in a power law. We want like some kind of like uh, uh, k to the some alpha dependence on like pk should have like k to the power alpha dependence on like k. And this is what we get in Baravasi-Albert network. So yeah, a lot to digest today, guys, but I hope you guys have gone through the lecture videos before coming to the session. Because then like it's just more like a revision for everyone. So this is the power law, and this is something which was also derived in the lectures. And because of this power law, like we say that like the network generated is scale free. So Baravasi network model, like you can also find out that it actually has a good clustering coefficient and also has a small world property. But more importantly, it follows power law, which is one of the most important things for us in real world networks. So Baravasi-Albert model follows power law, but there are some limitations to Baravasi-Albert model, which are like, so in this model, we assume that only one node gets added at a time, and it's difficult to apply if more than one node arise simultaneously. And similarly, it's a linear growth model because like at every time step, only one node gets added, which may not be realistic in many applications. And this predicts a fixed exponent in the power law distribution because like the exponent in the power law distribution here is actually just 1 by k cube. So it says that in the network in the real world network for which this model is applied, like the pk will be proportional to 1 by k cube. But note that in different kinds of networks, this value can be different. Like it can be 1 by k to the power 4 in some networks, it can be 1 by k square, it can be 1 by k to the power 2.5 or anything. But Baravasi-Albert model just predicts it to be k cube. So this means that this is not that much of a reality-related model, although it guarantees us some, like it has some sound theoretical guarantees and is like very creative. But like in real-world experiments, like for different kinds of networks, this exponent varies between 1 and 3. And this model does not capture temporal decay preference of node. It says that at any point of time, like a node has preference just corresponding to its degree, but like it does not take into account the time spent by the node in the network. Yeah. Okay. So maybe we should not get into like more models for now. I think all of these you can kind of search, go through the lectures. Maybe I'll just keep these slides here because like I think like since you guys don't have access to course slides right now, like I tried contacting the professor, but I did not get any reply. So for now, maybe I'll just keep these screenshots here because these screenshots can help you guys act as kind of like the slides. So like there is prices network model, then like all of these models together are called preferential attachment models. And yeah. So, and then there is something which is more relevant for like real world networks, which are vertex hopping models. So I guess we should not discuss all of these right now because it will be a lot to digest and we won't have time for discussing problems. So yeah, maybe I'll just leave this here and you guys can take a look at all of this. Although all of this has been discussed in the lectures, but maybe if you have gone through the lectures and just want a quick revision, you can just go through this. And I don't think we have any questions based on like anything after Baravasi Albert network model in today's session. Okay, then I guess we can get started. So now like I'll need you guys to be a bit more like proactive because I think like for all these questions, the answer is probably like already discussed in one of the slides. Maybe for not some of the questions, but for most of the questions. So yeah, I hope you guys can at least try to attempt these. So the question one says a network is said to follow small world property if like so there are four options. Average path length is proportional to log of network size inverse. Average path length is proportional to x e raised to the power network size inverse. Average path length is proportional to log of network size or proportional to e raised to the power network size. Okay, so Karpagam is saying that it should be proportional to log of network size. So yeah, good job, Karpagam. So this is actually the correct answer. This is what we discussed in the start itself. What do we mean by property? Like what do we mean by small? So small is just like average path length being proportional to log of network size. So the answer is option C, as discussed in the lectures. So good job, Karpagam. So these are a quick like just one questions for you guys. Like if you guys remember what we discussed. So then the second question is a giant component appears in a random network when the average degree of the network is greater than equal to 0.5, less than equal to 0.5, less than equal to 1, greater than or equal to 1. So yeah, would you like to answer this? Like we talked about this giant component in an ER network. Okay. So B, so Karpagam is saying B or D. Why B or D? Karpagam, like why B? Like if average degree is like less than equal to 0.5, like why is like okay, like again, like less than or equal to 1 or greater than equal to 1, like both of these cannot simultaneously be correct, right? Because these are contradicting. Or are you not sure between these two? Are you implying that you are not sure between these two? Oh, okay. Like one thing to note is like note that like if you are confused between less than or greater than, like just think of it intuitively as like the higher the average degree, like what does intuitively average degree mean? Average degree means like how many nodes is a vertex connected, right? And more the number of nodes the vertex is connected, the more will be the size of the component, right? So size of the component can only increase if you increase the number of nodes connected to a vertex. Like if you increase like degree of a vertex, then the size of a connected component can only increase. It can never decrease. So like if you have a connected component at like average degree equal to 1, you will also have a connected component at average degree equal to 2. Yeah, so that's why D is the answer. Like although like you need like this critical point of being greater than equal to 1 is important because like this comes out from calculations that it's not 0.5 or 1.25 or anything, but it's equal to 1. But note that always average degree should be like on the greater than equal to some constant side. Here the constant is 1, but average degree is, if it is on the greater side, then the network will become like larger. So this is like often deep. Again, as discussed in the lectures. So yeah, so this is like directly discussed in the lectures also, but just giving you an intuitive idea why it should always be greater than or equal to, never less than or equal to. Because as you increase the degree, the component size will always increase only. Okay, then we have like for the questions 3 to 5, like this is a common question, like, and this we have to follow answer for 3 things. So what are the distinct properties that are followed by the following network? This I just described to you guys. So what are the properties followed by Erdos network, random networks, like high clustering coefficient, small world property, or degree distribution following power? Yeah, so good job, Kirpagam. So it only follows like small world property as we discussed. Like ER networks only follow small world property, but they are still important for us because these were one of the earliest models proposed. So again, correct answer is only option B, as discussed in the lecture. This. Then what about Watt-Strogat's model? Like this was like, so Autosony network was just every edge being present independently. Then Watt-Strogat's model is the model which introduces like the concept of like ring lattices. Like it tries to merge the concepts of ring lattices and ER random networks. So we know that ring lattices had high clustering coefficient, like it went as high as 3/4, and ER networks have small world property. So yeah, exactly. Good job, Karpagam. So these will have smaller property as well as high clustering. So yeah. So for this answer is option A, comma C. So it's more than one choice, correct? As discussed in the, I think almost all the questions are here like these only, like these have been discussed in the lectures and you just have to answer them like. Like, so if you have gone through the lectures and gone through like even if you have gone through like today's session, like you have paid attention to today's session, like you'll be able to answer the questions today of today's session. And what about Baravasi-Albert model? What kind of properties does it satisfy? Okay. Okay, so it follow. Okay, so it follows power law. I think okay, maybe I also did not discuss like, or maybe I think when I'm saying to you guys now, I think I misspoke previously. Yeah. So yeah, so Baravasi Albert model actually like, so even I don't think this was discussed in the lectures or anywhere, but like it is important to note that. So maybe this question is like not exactly from the lectures, but it's important to note that only option C is correct. Like option C is correct. Like actually, like a Barabasi-Albert model does not have small world property or a high clustering coefficient. Like, I think previously I said that it had all the properties, but okay, like I think I just spoke wrong while saying it in flow. Like, for Barabasi-Albert model, like its degree distribution follows power law, but and its calculations were not done, although its calculations were not done in the lectures, and I don't think like it was discussed also, but like it does not have small world property or high clustering coefficient. But yeah, still it is a very important model because it was one of the first models to introduce degree distributions following power law. So only option C is correct, as BA model does not have small world property or high clustering coefficient. Okay, so yeah, this is why and why like an intuitive reason for why you can think that BA model does not have a high clustering coefficient is in BA model like it follows some kind like, so there are a lot of poor nodes and there are kinds of like rich nodes. So like there are nodes which have very low degrees and there are nodes like which have very high degrees. So nodes with very low degrees might be neighbors of some nodes. And so like for high clustering coefficient, usually you want to have like high degrees of nodes with respect to other nodes. Like the more uniform is the degree distribution between nodes, like high is like it's, I'm just saying this intuitively, but higher is the chance that clustering coefficient will be larger. Like in the ring lattice network, the clustering coefficient was high, but degree for every node was also like k only. So usually like more uniform degree distributions tend to have higher clustering coefficients. Like this is not exactly the case, but yeah, like but this is kind of an intuitive reason of why BA model does not have like small world property or a high clustering coefficient. For these properties, you need to have kind of like more uniform degree distributions. Although maybe like I'm not really sure, but there might exist networks which have all of these three things, but BA model definitely does not have. Like let's not get into the mathematics of it, but yeah, for BA networks only like option C is correct. Maybe I should mention this in the notes itself. Small world property or high cluster. So the only benefit, like, so there were three kinds of properties which we wanted, like high clustering coefficient, small world property, and like power law. So ER networks only gave us like a small world property. Lattices gave us high clustering coefficient, ring lattices, and then Watt-Stochastic, which combined ring lattices and ER networks, gave us both of these properties. But the third property of power law was remained elusive. This was given by Barabasi-Albert. But in their model, like it only had power law or the scale freeness, but it did not does not exhibit small world property or high clustering coefficient. So yeah. So again, this also has drawbacks. And that's why there are better models, even for the newer model like vertex copying model and so on. Okay, so yeah. So PA model does not have a high clustering coefficient. Now, like let's move on to the sixth question. So in ER random network model, so good job, Kirpa. Only option C is actually correct. Others you are not able to recollect because like yeah, they are not true actually. I did not discuss this previously. I don't think it was discussed in the lectures either, but yeah, this is the case. So now in the sixth question, like in ER network model, the clustering coefficient of a node is like, so this question I think also is like maybe more than one choice correct. So like what will be like, The clustering coefficient of a node in ER random network model is independent of P, dependent of P, dependent on node's degree, or independent of the node's degree. This I think we just discussed. Okay, so Kabagam is saying that it does not depend on degree of the node. So yeah, but and also like anything, it is dependent on P. So clustering coefficient, as we discussed, is actually almost equal to like P on P. Like in ER network, clustering coefficient of a node is equal to P, and so like it is like dependent on P. Like if it is equal to P, then it is dependent on P, right? And yeah, so it is dependent on P, and if it is dependent on P, like it's independent of the node's degree. Its formula is literally just P. So it is just dependent on P, independent of the node's degree. So good job, Kripa. So options B, comma D are correct as discussed in the lectures. Yeah. Now we have seventh question. So seventh question is more about like this Barabasi Albert network model. So where we said that like a node which has a higher degree will also tend to have like the new node coming in will also tend to have a larger probability of attaching to a node which already has a higher degree. Oh, okay. Oh, see, oh, okay, Kirpagam, I just saw. So thanks for the correction. So in the sixth question, it's us like in ER network model, clustering coefficient is not. Okay, so it is not independent of P. So the answer would be actually options A, because like it is not independent of P, it is dependent on P. And also like it is not dependent on the node's degree. So options A, comma C will be correct. So thanks, Kirpagam, for pointing out. Yeah. So that's why like options A, comma C, like B, comma D would be the answer if it was just clustering coefficient is, like if this not was not present, then B, comma D would be the answer. But since this not is present, then A, comma C will be the answer. Yeah. So these kinds of things, I think why I think I added this not is because like these kind of things you should take care of while like taking your weekly assignments also. In your assignment also, like in the quiz assignment, like it might be the case that the question asks for something like not, they add a like small not in the question. So even if you know the concept, like you might make a silly mistake like I did and have the question as incorrect, even though you knew the concept. Yeah. So principle of preferential attachment can also be thought of as. So I think we discussed the idea for this, and as Karpagam is saying in the chat, so good job, Karpagam. The answer is rich gets richer. So option C, as discussed in the lectures. Yeah. Like because rich guy, why is rich getting richer in this preferential attachment models? Because when a new node comes, it has a higher probability of attaching to a node which already had a high degree. So a node which already had high degree would be a rich node. So a node which was already rich would also have the probability of having new node added to it. So it would become even richer. So that's why these preferential attachment models say that rich gets richer. Because if you're already rich in degree, then the higher is the chance that you will obtain even more degree. So here rich is in terms of degree of the node. Like a node rich in degree will get richer in degree. This makes sense. Okay, then. So I think then we can move on to the eighth question. So eighth question is again just talking about, I think, the ER networks. So maybe I'll just put the question on the one page. So this we discussed like not as a plot, but in written, like we said that in ER networks, like this K is the average degree. So if average degree is less than 1, then the like small isolated components are there. If it is equal to 1, then connected component, a giant component starts appearing. And as we increase 1, and like as we start increasing the value of K, like the connected component size grows and grows. And as soon as like K becomes greater than log n, the connected component encapsulates the entire graph. So this ng by n is the value of like size of the connected component divided by the number of vertices in the graph. So you can see that with respect to like average degree, the size of connected component was initially 0 and it starts growing. Initially it starts growing very fast and then it slows down, and like after k greater than log n, like it just becomes almost equal to 1. So for this, okay, Karpagam is saying that this option D is correct. So this region 1 is called subcritical region. Yeah, this is what we discussed. Because, and then like this 2 is the critical point, because at this point the connected component starts appearing. And then there is a supercritical region where the connected component has been growing at a very large pace. And then there is this connected region at fourth, when the whole graph becomes connected. So yeah, good job, Kalpago. The answer is option D. So the answer is option D. Again, maybe this will also discuss in the lectures. Okay, so one more question. So what characteristic of the BA model distinguishes it from other random graph models? So we discussed some other models like ER networks and ring lattice networks. So what characteristics of BA model distinguishes it from other random models? So like let's look at option A. So each new node connects to a fixed number of existing nodes based on the node degree. So, and like all nodes have same number of links. New nodes are added at random without preference. Nodes can be removed and added back to the system. So maybe like option C and D are definitely not correct, because like new models are added with preference in BA model. Similarly, nodes cannot be removed or added back. Like if they're added, they stay there. So option C and D are definitely incorrect. And option B says that all nodes have same number of links. And option A says that each node connects to a fixed number of existing nodes based on the node degree. I note that like maybe I just skipped through this, but yeah. But in Barabasi network model, like all nodes are assumed to have kind of same degree. Like okay, maybe like not same degree, but like they arrive with same number of links. So maybe like saying that they have same number of links is also incorrect, but this is the maybe the correct thing. Like each node connects to the fixed number of existing nodes based on the node degree. Like did I write this here? Okay, maybe I did not write this here. Originates, closes, attach, say and all. Yeah, maybe like I did not write this here, but yeah. So so this was discussed in the lectures actually, that in BA model, like so whenever a node arrives and has to connect to some node, like it has a like fixed degree when it arrives. and based on that degree only, it connects to other nodes. So that's why this option A is correct. Like each new node connects to fixed number of existing nodes based on a node's degree. And note that all nodes have the same number of links is definitely incorrect, because we know that the nodes are following power law. Like the degree distribution is following power law. So number of nodes having like degree k is proportional to 1 by k cube. So for different nodes with different, so there are nodes which have different degrees. So option B is definitely incorrect. Option C says new nodes are added random without preference, which is definitely incorrect because they are added with preference. And option D is also incorrect because nodes cannot be removed from the system in a BA model. So option A is correct. So only option A is correct, as it is assumed in the BA model that every node has the fixed degree at the point of its arrival. So the degree of a node will change, but as soon as a node is arriving, that's when we call it the new node. Its degree is actually fixed. Yeah, and this is what is assumed in the PA model. And this was discussed in like derivations when we were in the lectures when there were derivations based on PA model. So you can look at all of those. But yeah, this is something which is important. Yeah. Okay, then the last question for the day maybe. So this is something like which I would like you guys to think about for a couple of minutes. So suppose you are given the following formula for clustering coefficient of a Watt-Stogas model. So this is the formula for clustering coefficient. So it is 3 times k minus 2 divided by 4 times k minus 1. And if you are given this clustering coefficient formula, determine the minimum and maximum values of the clustering coefficient. So you're given the formula for clustering coefficient as follows: 3 times k minus 2 divided by 4 times k minus 1. And you have to find out the minimum and maximum values for this. So Karpagam, would you like to try this out? Like I would like you, all of you guys, to try this out for a couple of minutes. It's not too hard of a question. Like, so you are given just, so it's like, even if you don't know what a Watt-Stogas model is or anything, you just need to look at this formula, which is already given, and see like what's the maximum value of this CCWS in this formula. Like what's the maximum value and what's the minimum value it can take. This, what's the maximum and minimum values that this function can take. Now it's like not even a like social network analysis question. It's just like basic high school math question. Like this is a function of k. What's the highest value and what's the maximum and what's the minimum value that it can take? Come on, guys, like it's just high school math. So Karpagam is saying option B, 0, 3 by 4. So yeah, good job, Karpagam. So it indeed is correct. Like, so this function takes the values between 0 and 3 by 4. And why is this the case? So maybe we'll just discuss this. So maybe I'll just write option B is correct. And why is this the case? So we know that like the value of k will always be greater than 0, right? K cannot be like, k can be like greater than equal to 0. K cannot be less than 0 because like number of nodes can never be negative, connected nodes. So what's the value that this function takes when and also like maybe we'll just assume that k is actually greater than equal to 2, because we have like k by 2 forward and k by 2 backward nodes. So you cannot have k equal to like 0, then the network is nothing but like disconnected network. And if you have k equal to 1, then like it will just be like half forward and half backward nodes, which is not possible. So k will always need to be even, and like the minimum value that k can take is greater than equal to 2. Since k is always even and positive, the minimum value that k can take, I'm not talking about the CCWS value, but about k can take is 2, or maybe just I'll just write this k is greater than equal to 2. So what this means is if k is greater than equal to 2, so note that this term can like, so this term will always be positive. First of all, like CCWS will always be positive. Like it cannot be negative, at least, because like if k is greater than equal to 2, then this terms cannot be negative. But note that at k equal to 2, what's the value that this CCWS takes? So at k equal to 2, this becomes 3 times 2 minus 2 divided by 4 times 1. So CCWS is nothing but 0. So the minimum value that CCWS takes is like 0. Since CCWS can never be negative, hence its minimum value is 0. So first we have that minimum value 0, and now we want to find out what's its maximum value. So note that how to find out the maximum value for this function. So to find the maximum value for CCWS, so what do we do? So we just rewrite this formula maybe. So this 3 times so this is nothing but CCWS is equal to this thing. Or maybe should I write this as an equation? Like it will be much easier to visualize. Just a second, guys. So maybe I just write it here. So CCWS is equal to 3 times k minus 2 divided by 4 times k minus 1. So this is the formula for CCWS. And now, like, how do I say like what will be the maximum or minimum value for this? So I can't really say much about it right now, because as you increase k, both numerator and denominator increase. So it's not really easy to tell like how will this function change when k changes. So what we do is maybe I try to rewrite this kind of thing. And how do I rewrite this? So maybe I just do so I write this k minus 2 as k minus 1 minus 1. And what this helps us to do is like it helps me write this as like k minus 1 minus 3. Like this is what this function is like. 3 times k minus 2 is just 3k minus 6, which is equivalent to writing it like this. But now I can break this thing into 2 parts, and k minus 1 will cancel out. And they can only cancel out because k is greater than 1. Since k is greater than 1, these values can never be 0, so they will cancel out. So this will become something like 3 by 4 minus, because this becomes like k minus 1 cancel out, and this becomes 3 by 4. And the remaining part is 3 by 4 times k minus 1. So this is the formula for CCWS. And now you can easily see like how it changes as we increase k. So as we increase k, this whole thing which is in this whole thing decreases, and since this whole thing decreases, since this was the negative, the whole term actually increases for CCWS. So what this means is Hence, CCWS is an increasing function of K. Maybe I'll just write it here. Yeah. So as as K becomes larger, as K tends to infinity. So basically, as K becomes larger, this value becomes like CCWS becomes like 3/4, because this whole term tends to 0, and 3/4 minus 0 is 0. CCWS tends to 3/4, and hence 3/4 is the maximum value of CCWS. So yeah, so that's why like 3/4 is the maximum and 0 is the minimum, as Karpagam already said. So good job, Karpagam. Like this is the correct answer, and this is how. Like although this was directly discussed in the lectures, that 3/4 is the maximum, but this is how you kind of like derive it mathematically. So you need concrete mathematics to like actually say this. Like minimum can be found out easily by just putting 2, and you can find the value as 0. But for maximum, you actually need to show that maximum is obtained at K tends to infinity, and this is just done by like rewriting this fraction as in terms where like it's easier to interpret. So yeah. Okay, so I guess this was it. This was all the questions which I had for the day. So yeah, again, like I think a very tiring session. Like we just like most of the questions are based on like the basic definitions. So if you attended the session, and the lecture, you would have gotten most of the questions like as Karpagam did, except maybe a couple of questions. And other than that, we mostly discussed like not everything, but a lot of main things which were covered in this week's lectures. So there are a lot of models, but we try to cover the most important ones first, and then like yeah. Still, I'm leaving the other slides here only for you guys to maybe look at it if you guys want to look at it later. So yeah. So this is it. What I had for the day. If there are any. Okay, so Karpagam is saying, can you help solving the last question in the assignment? Okay, Karpagam, so the thing is, I don't think we are actually allowed to provide hints like for the assignment questions. That's why like we can discuss questions similar to the assignment, but not the exact assignment questions. Maybe like after the deadline of assignment is over, we can definitely discuss, but I think I can't discuss it right now. So sorry for that. But other than that, anything related, maybe like anything related to today's session, like if there are any doubts related to today's session or previous session, feel free to ask in chat. Like we can have a couple of doubts, like 2-3 minutes before closing. And if there are no doubts, like then maybe we can also close the session. Okay, I don't see anyone typing in the chat right now, so I'll assume that there are no doubts. So then I guess we can wrap up. So thanks a lot for joining the session, guys. So I hope I'll see you guys next week also in person, same timing, Monday 6 to 8 p.m. And yeah, till then, goodbye, guys. So I'll close the recording and you can leave the session. Thanks a lot for joining.